let's review what we've been doing last time. And last time we have discussed functions of one variable. So that was the case. That's the usual case. Domain of this function is contained in this space R1. So maybe domain of this function is some interval. And here, difference is that domain of this function is contained in this two-dimensional space R2. So here, the domain is some subset of the two-dimensional space. So let's say when the function f is given, then the function in this context is a function of one variable. So we can say f of x. Some function f is given, and maybe that's the graph of this function. Here, the function is also given, and it's a function of two variables. So we have the situation that the function f depends on two inputs. Let's say x and y. X and y. And if you take any input, i.e. any point, and to be more specific, any point which has two coordinates, the first one is maybe x and the other one is y, then this is the corresponding output. And if you collect all those outputs, then that will give you a surface in a three-dimensional space, which is the graph of the function. The key point of calculus is, well, two things. To compute derivative of a function, and the main application of derivative is to find the tangent line to the graph of the given function. That's one thing. And then to find the minimum maximum value of this function. So if we have some point x0, in the domain of this function f, well, then we have this function f given that this is the point f of x0, which we can call for simplicity 1, 0. Okay, so we have this point on the graph of this function. So if the function f is given, then I can compute derivative of this function f at any point x. In particular, if I take derivative of this function at this point x0, if I take derivative of this function f at this point x0, this is the interpretation of this number is that this is a slope. This is the slope of the tangent line to the graph of this function. So the slope is exactly this one. This is the slope. So now you can consider this function y equals, let's say the number would be f prime of x0, and then times x. So this is exactly the straight line that goes through 0. Notice that this function, when x is 0, then the function is 0. So the function goes through 0. So this is exactly this line. This is exactly this line, which is parallel to the one of interest, but it doesn't go through the point that we want to. So for now, this is just this function y equals f prime of x. So now what we can do, we can shift this function to the right, or to one side to be more specific. So we can consider this function y equals f prime of x0. Then the factor that's responsible for the shifting is the factor x minus x0. Notice that if x is equal to x0, then this is equal to 0. So the function will look like this. And last thing to do, we want to shift this function up to the given point, to the point f of x0, and simply the summand that's responsible for the shifting would be the number f of x0. So I'm going to take this function, and I'm going to shift this function to the given point f of x0. And specifically, to this function, I'm going to add f of x0. This number f of x0. So f of x0, and then plus this portion of this function. So this is, what is it? This is f prime of x0 times x minus x0. And you can think of this times as a dot product, except that it's one-dimensional. So it's exactly the same as multiplication. Okay, so you can call this function L, and that's a linearization of this function f, and the function looks like this. This is the linearization of this function f. So really, this is the tangent line to the graph of this function at this specific point. The generalization of this is the following. So we have a situation that now I have a function of two variables, x and y, and I'm going to fix a point in the domain of this function. So maybe the first coordinate of this point is x0, and the second coordinate of this point is y0. So we have this point, and we have a function. So the function is f of xy. That's the function. I want to compute derivative of this function with respect to x. Derivative of this function with respect to x is a function of x and y. And also I want to compute derivative of this function with respect to y. This is also a function of x and y. This is exactly what we did here. We have computed derivative of this function f, and then we have evaluated this derivative at this point x0. So we'll do this in this case. I'll take this function fx, and I'm going to evaluate this function at this point x0, comma y0. And I'm going to take the other function fy, and I'm going to evaluate this function at x0, comma y0. And then I can take the vector, because I have two numbers, I can take the vector. So this is the vector of partial derivatives at this specific point, and then I can shift this, or I can consider the dot product with x minus x0, x minus x0. That's the first coordinate of this vector, and the other one would be y minus y0. And I'm going to add to this thing f of x0, y0, f of x0, comma y0. Okay, so this function, this function is a function of two variables x and y, and this is exactly the linearization of my function f at this point x0, y0. Okay, so if we, this is the dot product, and if we multiply those two vectors, then this is exactly what we get. This is f of fx times x minus x0. This is fx times x minus x0, and then this vector times this one, that will give me this. That's the linearization of this function. And one way how to think of this is that this is the tangent plane. This is the tangent plane to the graph of this function at this specific point of interest. Okay, example, very quick example. Let's find the linearization of a given function at a specific point, or the same, let's find the tangent plane to the surface. This is the surface, that's a given surface. Z equals x times the exponential function to the x times y. So we can call this function, f of xy, for example. We can call this function f of xy. That's the function x times the exponential function to the xy. This is a function of two variables. It does depend on x and y. So x and y are the independent variable in this expression, and I can take any x, I can take any y, and when I substitute to the function, that will give me the corresponding output. And when this is how the graph of this function f looks like. So this is how the graph of this function f looks like. And I have also a given point, 2, 0, 2. So on the x-axis is 2, on the y-axis is 0, and then on the z-axis is 2. So that's the point. That's the point, and maybe call this point B, for example. That's the point B. And what I have to do is I have to find a tangent plane that touches this function at this one point. So this is the plane. Well, geometrically, but I want to find an analytic expression for this tangent plane, which really is a function of two variables as well. So let's do this. The function is f of xy. Okay, so let's compute. Let's see, what ingredients do we need to find the equation of the tangent plane? Maybe first of all, let's compute derivative of this function f with respect to x. So this is going to be a new function of x and y. This is going to be a new function of x and y. So let's see, what is the derivative of this function with respect to x? This is a product of two functions, so I have to use the product rule to compute derivative of this function with respect to x. meaning that I'll be thinking of y as 2, for example, 2, or any constant. But just for a second, let's think of this y as 2, or any other constant. But let's compute derivative of this function now with respect to x, thinking of y as that would be, for example, 2 or any other constant. So this is the product rule. So I'm going to take derivative of the first function. And when I say prime, I'll mean derivative with respect to x. I should indicate this somehow in the notation. However, we can just mention. So I can take derivative of the first function and then times the second function itself. So times e to the xy. And that's only one step in this computation of this derivative. The second one being take the first function, whatever the function is, so x, and now take the second function and take derivative of the second function with respect to x. Again, I should indicate this probably using a different notation, but let's say we compute derivative of this with respect to x. Okay, so what is derivative of this function x with respect to x?
1.
Excellent. 1. So this is 1 times e to the x, y, and then plus x times, okay, derivative of the exponential function is the exponential function itself, e to the x, y, but now I have to take this exponent x times y and compute derivative of this with respect to x. This is what we are doing. Okay, so let me rewrite everything. So this is 1 times a function, that's just a function. The 1 doesn't contribute in any way. So this is the exponential function to the xy. And then plus, let's see, this is x times y. What is the derivative of x times y? Think of y as a constant, for example, 2, like 2x. What is the derivative of x times y with respect to x?
Y.
Excellent. So x times e to the xy, and then times y. Okay, so I can simplify this a little bit, and I can say this is the same as e to the xy, and then plus this is x times y times e to the xy. Okay, so now we have the derivative of my function f with respect to x. Let's do the same computation, and let's compute derivative of the same function, but now with respect to the other independent variable, which is y. Let's compute derivative of this function f with respect to y at any point xy. Okay, so this is, okay, so now think of x as a constant in this formula. So x equals constant. For example, 2. You know, for example, 2. Then let's compute derivative of this function with respect to y. Y is the independent variable. So this is going to be x times, this is e to the x times y. But now I have to take the x times y and compute derivative of this, but with respect to y. Derivative of this with respect to y. So that will give me x times e to the xy, x times e to the xy, and then, okay, what is the derivative of x times y with respect to y?
X.
Exactly. So times x. Excellent. So this is equal to, well, x times x, this is x squared, and then times e to the xy. And that we are essentially done, because the only difficult part, or the only part that involves some calculation, is computing partial derivatives. Once we have partial derivatives, then we can very easily find the equation of a tangent line, the tangent line to the function at the specific point. So now we'll have to, let's see. Now we'll have to see what those functions are equal to at this point of interest. So the point was 202. The point was 202. Okay, so let's compute the x derivative of my function f at xy, but at 0. At 2, 0. Okay, so what is this function equal to at 2, 0? Well, this is 2 times 0 e to 0, this is 1. And then this is 2 times 0, this is 0. Okay, so this is 1. And what is this function equal to? What is the y derivative of this function f equal to at this point 2, 0? So that's a question for you. Okay, question for you, what is this equal to at 2, 0? Here's the formula for the function f y.
4.
Excellent, this is equal to 4. So we are done at this point, because now what we can do is, okay, this is the first partial derivative. That was the function given. That was the given function. The point of interest was 202. And then what we did, we have computed the first derivative of this function. And we have done that on the previous, just 1 second ago. And also we have computed the y derivative of this function. That's the fy. Okay, those are the partial derivative. This is the partial derivative with respect to x. This is the partial derivative of my function with respect to y. Now I have to evaluate this function at 2, 0. So we have also done that just 1 second ago, that's 1. And we have to evaluate this function at the point of interest, which was 2, 0. So fy at 2, 0 is equal to 4. So you just told me it's equal to 4. Now what we have to do is we have to look at the vector of partial derivatives. So this is going to be 1. This is the partial derivative of my function f at this point 1, and the other one is at 4. This is 4. This is the partial derivative of my function y, of my function f with respect to y at 2, 0 equals 4. Now let's look at the dot product. And then we have to take a vector of the point was, remember the point was 2, 0, 2. Okay, let me just check. The point was 2, 0, 2. So we are going to take, well, x minus x0, which is x minus 2, and then y minus y0, which is y minus 0. Okay, this is the dot product of two vectors. What is this? This is the partial derivative of my function f with respect to x evaluated at this point 2, 0. That's the one. And what is this component of this vector? That's simply the y derivative of my function f at this point 2, 0. So that's 4. So that's 4. This is that's the 1. And this is 4. Okay, this is the vector of partial derivatives at this specific point. This is the translation. This vector is responsible for the translation. And there's one more ingredient that's responsible for shifting this function, this plane, up and down, which is I have to add to this f of what point? F of 2, 0. F of 2, 0. Okay, and that's the linearization of this function because we can compute the dot product. So that was the function L of xy, and that's equal to this. This is the tangent plane to the function f at this specific point. So let's see very quickly, what is f of 2, 0? Well, if x is 2 and y is 0, what the function is equal to f of 2, 0? Well, this is x is 2, and this is x times z, this is 0, e to the 0 is 1, so this is 2. Okay, so this is 2, and then plus, this is in a product, so this is 1 times x minus 2, 1 times x minus 2, and then plus 4 times y minus 0, so 4 times 1. Okay, so this is 2, so this is equal to 2, and this is plus x, and then minus 2, and then plus 4y. So when we simplify that, that will give me just 2 and minus 2, those will cancel. That will give me x plus 4y. Okay, so the equation is the tangent plane is x plus 4y. So the tangent plane is x plus 4y. X plus 4y, z equals x plus 4y. This is the tangent plane to the graph of this function at the specific point. Okay, so something that's called the gradient of a given function. And the gradient of a given function is defined in the following way. Just a definition. It's not that this is important. It's just a piece of terminology that they use very often. So when we have a function of two variables f of x, y, when the function f of x, y is given, f of x, y is given, then I know that I can compute the x derivative of this function. This is also a function of x and y. And I can also compute, on one hand side, I can compute the x derivative of this function, and also I can compute the y derivative of this function. And this is also a function of x and y. And then when we can form this kind of matrix, either we can think of this as a 1 by 2 matrix or as a vector. So the first component of this vector is the x derivative of my function f at any point x, y. And the second component of this vector is the y derivative of this function f, also at any point x, y. And when we consider this as a vector or as a matrix, we can think of this in either way, then this is called the gradient of a given function f at a point x0, y0. And notation for this is gradient of this function f. And notice that this depends on x and y, and so does this. So we have to indicate that this vector depends on x and y. Okay, so the gradient is simply the vector of partial derivatives. Gradient is simply the vector of partial derivatives. So for example, let's take this function f of x, y equals, that's the function that we just mentioned 1 second ago. F of x, y equals x. So let's take this function f of x, y equals x times, and then the exponential function e to the xy. Okay, and we have computed the partial derivative 1 second ago, so we won't be doing this again. But the x derivative of this function f was this one. That was the x derivative of my function f. Also, so that was the x derivative of this function f. Also, I can compute the y derivative of this function f, and we have also done that just 1 second ago, so we won't be doing this now. But this is the y derivative of this function f. And now I can consider the vector that consists of those two functions. The first component of this vector is going to be the x derivative, the function. Okay, so the vector is this one. And the first component of this vector is the x derivative of this function. And this is the x derivative of this function. And the second component of this vector is the y derivative of this function. Y derivative of this function. That's gradient of this function. Now, how to think of this? Why does my, okay, so this is the gradient of this function f at any point x, y. But now let's see specifically what this gradient is equal to. What this gradient of this function f is equal to at specific point, maybe to 0. To 0. So that will give me a vector. When x is 2, y is 0, then this is 1 and this is 4. So the gradient is this. This is the gradient of this function f at this point 2, 0. That's the vector 1, 4. What does this mean? How to think of this vector 1, 4? Well, this is the direction when the function is essentially increasing the most. So let's get back to the very first slide that we mentioned today, And the idea was that, okay, if I have this function f of xy, if I have this function f of xy, and if I fix some point in the domain of this function, so maybe this is point x0, y0, then I would like to know the equation of this tangent plane to the graph of this function at the specific point. So we know that this equation of the tangent plane would be the following. I compute the x derivative of my function f at this specific point x0, y0, x0, y0, and then I compute the y derivative of my function f at the same point, x0, y0. That's the vector of partial derivatives at this specific point. Now we do the dot product with x minus x0 and then y minus y0. And then I have to add to the whole thing the value of this function f at this point x0, y0. So f of x0, comma, y0, and this is exactly the linearization of this function. This is exactly the equation of this plane. But now, just so we can rewrite this equation, because what we can see here, this is exactly the gradient, of this function f at this specific point x0, comma, y0. This is the gradient, it's a vector, so I can take the dot product with this vector x minus x0, and then y minus y0. Okay, and then I have to add to the whole thing f of x0, y0. Okay, so this is exactly this. And as a function L of xy can be written that way. This is the tangent plane to the graph of this function f at this specific point x0, y0. Okay, so essentially think of this plane as this one. This is the plane. This plane and this plane is a tangent. It's touching the function just at one specific point. And well, essentially that's exactly the same equation, except that we have rewrote this equation using the concept of gradient. Now, okay, so gradient is a vector, and if the function looks like this, okay, let's say, even looking at this graph of this function, how the gradient would look like. So let's see. What we could do is, let me just go to the first slide. Maybe I can use better this picture. So what we can do, we have this point, and we can look at the level curve of this function. So that would be a circle. That would be a circle. And then we can kind of project this circle onto the xy plane. We can project the circle onto the xy plane. That's the level curve of this function. And the gradient vector, we know that this gradient vector would look like something like this. Would look like something like this because the function is increasing in this direction. That's the intuition. Of course, we could compute this formally when we have expression for the function, but that's the intuition of the gradient vector. So here's another example. Okay, so when the function looks like this, notice one thing. The gradient vector at this point would be 0, 0, because the tangent plane to the graph of this function is flat. There's no slope. And actually, this will give us to the next section that we would like to mention in this class, how to find the maximum value of a function or how to find the minimum value of a function of two variables. And the idea is that we'll use the idea of the tangent plane, because let's say the function, that was the function f of xy. Let's say that was the function f of xy. How would you find the maximum of this function? Looking at the graph is kind of obvious. While it's here, you can say here it is, and this is the maximum of this function. But how would you find the maximum of this function formula? You would like to look at the partial derivative of this function f with respect to x as a function of x and y. And also you would like to look at the partial derivative of this function f with respect to y. And then you will like to see at what point xy, those two values are 0. Remember, when that was a function of one variable, first of all, you'll look for critical points, and that's the point when the derivative is 0. That's the point when the derivative is 0. That would be exactly also a critical point, because here, not only, well, the derivative concept is we'll have to specify that the x derivative is 0 and the y derivative is 0. So to find the maximum of this function, we'll be looking at this kind of plane, because this kind of plane is a flat surface. And at this point, exactly, this is the maximum of this function. So, or this is another example. This is just a function f of xy. And this is a few gradients of this function. So looking at the field of gradient vectors, you can say something about the function. So for example, see the gradient vector at 0, 0 is just 0. But when you look at this vector, this is a gradient at some specific point, and the function is increasing in this direction. And then when you look at, for example, maybe this vector, then you will see that the function is also increasing in this direction. Looking at gradient field, you can say something about the function. And in particular, this is a very convenient way to say where the function is maximum when the function is minimum. Looking at the gradient field, you can see that this is a kind of minimum because the function is going up, up, up all the way, and this is kind of like the minimum of this function. And indeed, this is the minimum of this function. So now, let me just recall for you second derivative test, but that's the one that you know. That's the simple one. That's the one that you know from Calculus 1. Let me remind for you this test. What this test says is the following. So you have some function f. Let me take this function f of x equals, let's take a simple function, maybe x squared. Okay, how does the function x squared looks like? This is the x-axis. This is the y-axis. So the function f of x equals x squared looks like this. It's a parabola, you know? It's a parabola. That's how the function f looks like. Okay. I'm going to ask you this question. Just looking at this picture, what is the minimum value of this function? What is the minimum of this function?
0.
Excellent, is 0. See, the function was very simple. We could just say right away, but we have this very beautiful tool, which is the first derivative test and second derivative test, because when the function was much more complicated, then we wouldn't know where the function is minimum maximum. That would be much more complicated. So for that, what we do is when I have this function f, well, this function f, we know that the minimum is here at its 0. But what we do, we compute the derivative of this function, f prime of x. Okay, could you tell me what is the derivative of this function?
2x.
Excellent, 2x. And let's sketch the graph of this function 2x very quickly. So this is a function 2x. This is the function 2x. And then, so how do you find critical points? Critical points are exactly the points where the derivative is 0. So you have to solve this equation 2x is equal to 0. What is the unique solution of this equation 2x equals 0?
0.
Excellent. So 0. So 0 is a critical point. And now how do you know that at 0 is minimum, maximum, or maybe neither of those two? You look at the second derivative. Okay, and I'm going to ask you this question. What is the second derivative of my function f equal to?
2.
Excellent, 2. And then what you do, you look at what the second derivative of this function is equal to at this critical point at 0. Well, what is my second derivative of this function f at 0 equal to? The function is constant.
2.
Excellent. The function is constant. Doesn't really depend on x. It doesn't have to be always that way, but the second derivative is equal to 2, and 2 is a positive number. So with the second, so we have this case. When the second derivative of my function f, when the second derivative of my function f is positive, at the given point, at the critical point, when the second derivative of this function f is positive, strictly bigger than 0, and that's the case, then my function has a local minimum at the critical point. So at x0 equals 0, because that's my critical point. At x0, at this point x0, the function f, the function f, which is exactly this one, has local minimum. If we get the case that the second derivative is less than 0, then my function has a local maximum, and that's the case when this derivative is bigger than 0, then we have local minimum, and so on and so forth. Okay, now big question is this: how to generalize this to function of two variables? What do you mean? What do we mean by second derivative of the function when the function has two variables? Okay, this is exactly the point what I want to mention now. So let's say that we have a function f, but now my function f has two variables. So I have a function of x and y. Okay, I have a function of x and y. Okay, if I have a function of x and y, I can compute the x derivative of this function. So this is also a function of x and y. And I can compute the y derivative of this function f. In other words, derivative of this function f with respect to y. And it's a function of x and y as well. And it's a function of x and y as well. But okay, if this is so you can compute the x derivative or the y derivative. But if this is a function of two variables as well, if this is a function of x and y, then you can take this function fx and you can compute the x derivative of this function, or you can take this function fx and you can compute the y derivative of this function. So those are the second partial derivatives of this function f. And okay, so this function depends on x and y, and so does the other one. The same thing is here. This is a function of two variables, x and y. And if this is a function of x and y, I can take this function fy, and I can compute the x derivative of this function. Or if I take this function fy, I can compute the x derivative of this function. So now I have four functions. Just given function f, now I have four functions: fxx, fxy, fyx, and fy. So sorry, this is y with respect to x, and this is with respect to y. Okay, so I have four functions, f, y, y. And I can consider the following matrix. And so, okay, so the 1, 1 entry of this matrix would be fxx. The 1, 2 entry would be fxy. And then the 2, 1 entry would be fyx. And then finally fyy. Okay, so this is a matrix of four functions. Okay, so here's the matrix of four functions. And notation for this matrix is h. Of course, it's a function of x and y. So the notation of this matrix is h of xy, and then the matrix is usually called the Hessian matrix of this function f at this point x, y. Notice one thing. We mentioned this the other day, but when all the derivatives are continuous, then this entry of this matrix and this matrix of this matrix would be the same, would be equal. They're almost in 99% of functions, this is not always true, yes, but in 99% of functions, those entries would be equal. So then I can compute the determinant of this matrix, determinant of this matrix H, which is simply this times this, which is simply f of x fxx times fyy minus, well, this times this, but we'll be assuming continuity, then this is equal to that, so this is simply minus fxy and then squared. Okay, so call this determinant B. This is exactly f of x, fyy, minus, the reason we have squared here, because we're assuming continuity of partial derivatives. And this is exactly the analog of the second derivative of the function f. And here, when derivative of this at a given point a, b. So now we have this situation, I have some function in three variables, so some function f, some surface, and I have some point, maybe a, here's a, and b. And I want to know this, let's say this is a critical point, meaning that the first derivative and the second derivative is 0. Okay, so how do we test if we have local minimum, maximum, or a saddle point, which looks like this? This is exactly what this test says. So when the derivative is positive, and the one entry of this matrix is also positive, then the function f has a local minimum at this point AB. If we have this situation that the derivative is positive, but the first entry is negative, then we have the local maximum of this function. When the derivative is just negative, then we have a saddle point, and if this is equal to 0, then essentially the test is inconclusive. We'll have to find another method how to see what we have. So here's an example of the function. Let's say this is the z-axis, something like this. Okay, and then here at this point we'll have a local minimum. At this point, when we have the coordinate system, then we'll have a local maximum. This is local maximum of this function, so that's the case when the derivative is, the determinant is positive, but the first entry is negative. And here we have an example when you have a saddle point. So the function will look like this. So at this point, we don't have minimum, we don't have maximum, because notice the function doesn't have minimum, It looks like a saddle, and from that reason, they call this a saddle point. So a quick example, take this function f of x, y, take this function f of xy. Okay, this is the last example. Take this function f of xy, and we know that this function has a minimum at this point. No problem, we can see that minimum of this point. But let's compute the, so f of xy is the function x squared plus y squared. Okay, let's compute the x derivative of this function f at any point xy. Well, the x derivative of this function is 2x. And the y derivative of this function at any point xy, the y derivative of this function is, what is the y derivative of this function?
2y.
Excellent. So the y derivative of this function is 2y. Okay, now let's compute, let's take this function f of x. I won't write this xx just to keep the notation simple, but really we should. But okay, let's compute the x derivative of this function and the y derivative of this function. So the x derivative of this function is 2. And the y derivative of this function, there's no y, so it's 0. Okay, let's compute the x derivative and the y derivative of this function fy. So let me take this function fy and compute the x derivative, and let me take this function fy and compute also the y derivative. Okay, with respect to x, this is 0. And notice one thing, not surprised, the mixed part, excuse me, the mixed partial derivatives are equal, not surprised, because the mixed partial derivative is equal. And what is the y derivative of this function? 2. Okay, so let's look at the Hessian matrix. So this is fxx, fxy, fyx, and then fyy. So in my example, the Hessian matrix is going to look like fxx is 2, fxy is 0, fyx is 0. Well, of course, it's symmetric, so those two entries are the same. And then 2. Okay, and now let's see. Determinant of this matrix H, determinant of this matrix H, if you don't remember what determinant is simply this number times this number minus this times this. So determinant of this matrix is 4, and it's positive. And I have to look at the first entry of this matrix. The first matrix is fxx, which is equal to 2 in my example, and it's also positive. So because those two things are positive, the determinant of this matrix is positive, and so is the first entry of this matrix, then at this point 0, 0, we have minimum, local minimum. And by the way, the critical point of this, the critical point is 0, 0, because I have to solve this equation 2x equals 0 and 2y equals 0. So the only solution of this system of equation is x equals 0 and y equals 0. So the point 0, 0 is the only critical point. The point 0, 0 is the only critical point of this function f. And then I have to test this critical point for a minimum, maximum, or the saddle point. In this example, we have determinant is positive and the first entry is positive as well. So we have minimum. So we have local minimum. See, determinant was positive, and also the first entry of this matrix, which was 2 in my example, was also positive. So that's why we have at this point local minimum. And in fact, it's a global minimum. But, okay, so last example to mention is this one. Last example to mention is this one. So the function f of xy is given. Excuse me. The function f of xy is given. And I want to find the local minimum maximum of this function. So first of all, compute the first derivative of this function with respect to x and this first derivative of this function with respect to y, and solve those two equations, fx equals 0 and then fy equals 0. I need to solve this equation because I need the critical points. When I solve, then I will get 3 critical points, 0, 0, 1, 1, and -1, -1. Those are the critical points at this point, and this one, and this one. And we'll see that at this one we'll get minimum, and this one will get a minimum, and this is the saddle point of this function f. Okay, so then construct the Hessian matrix of this function f at those 3 points, and use the test that we just mentioned. That will give you that at this point we have a local minimum, and this point we have a local minimum, and this is a saddle point of this function. Okay, so